All right, well, now we've seen our basic objects, the arrow relation, functions, and arithmetic. I want to get back to the arrow relation just to see what happens when functions and arithmetic become involved, and see that we recover exactly our old definitions once we do so. To start off, let me lead you through again. 1 plus fits into 1 plus minus y. Well, blue's leader, red's chaser. No matter how far the leader squeezes for any epsilon greater than 0, right? The chaser can squeeze, far enough. There exists a delta greater than 0, squeeze far enough, so that that red slice fits into the blue slice. The red points hit the blue target. Okay, in fact, fit inside the blue target. Quantifying it, the red points, if you want to call them x, are the points that lie between 1 and 1 plus delta. They need to hit the blue target, meaning those same x's need to be between 1 minus epsilon, 1 plus epsilon, but not equal to 1. Okay? That was 99% of the way to the definition, standard definition of limit. All the logic is there, none of the complicated algebra. Okay? So, presuming that's been reasonably well understood, we can then move on to functions, and the game doesn't change much. Well, what's 2 plus squared? Well, here without the graph behind you, you can still animate the result and see what you think the answer should be. It looks to me like the answer is 4 plus. Whoops, that's not a 4. 4 plus. Great. Now notice it's not an exact fit, but if you think through the definition of this arrow relation, everything fits in nicely. The target is still a plain old 4 plus. So quantify it with epsilon as usual. No matter how far that target squeezes, what should I be able to do? Well, the chaser is squeezing as well, and the basic object in the bottom of that is the 2 plus. I should be able to squeeze my 2 plus far enough, not so that the 2 plus hits the target, but I take the elements of the 2 plus and I square them. These need to hit the target. Okay? And if I squeeze, let me zoom in a bit. If I squeeze this far, I'm good. Okay? I was given an epsilon. I found a delta. I took all of those numbers in the top slice, all those numbers between 2 and 2 plus delta, those are my x's. I squared them. My x squareds live here. And those numbers x squareds have to hit this target, which I draw as usual. X squared needs to be between 4 and 4 plus epsilon. And that's the definition. The only difference in this definition is that in that very last step, you've applied the function to x instead of dropping it straight down. So when you do these proofs, if you do the proofs, they're certainly more complicated because of the algebra. But the logic isn't. The logic you've seen before you get to the functions, before you get to the arithmetic, and you simply apply the same logic with one extra step, which is applying the function. If you do arithmetic, it's the same game, but there's now 2 objects, so it's a little bit more complicated. And again, you don't necessarily want to prove all of these things, but you could. 1 plus 2 minus fit into, well, what did it look like it was? It was 3 plus minus dot. So let's see what the definition would look like. Prove it or not. Here, what would the definition look like? Well, start with the leader. The leader's still 3 plus minus dot. The leaders are pretty much almost always basic near numbers, basic objects here. So quantify it as usual, epsilon. No matter how far the target squeezes, right? What should I be able to do? My 1 plus my 2 minus should squeeze, and they're both small guys, so I want to use delta twice, so I'll use subscripts. There should exist an amount to squeeze my 1 plus and my 2 minus, a delta 1 and a delta 2, so that what? Not so that the original point's up top. If x is in my top slice, 1 plus, and y is in my second one of 2 minus, not anything that x and y do individually, but if I add them, add those 2 numbers, I get x plus y, that x plus y hits the target. So read the rest of the definition. If x is in the top red and y is in the other top red, then x plus y, the middle red interval, hits the target. X plus y should be between 3 minus epsilon and 3 plus epsilon. Now that's a long definition. It's actually not hard to prove this one if you're comfortable just doing some epsilons and deltas, but you wouldn't have to. You can write the full definition out, and if you do, the definition matches up exactly with the standard definitions. But even if you don't want to, with no symbols and no logical with no well, symbols, I guess, no symbolic definition, you can still understand what this means. If I squeeze the target far as I like, then the 1 plus and 2 minus can squeeze down enough so that the result fits inside. The standard argument I made before still holds. You can have a picture of all the concepts you've seen before in your head, and those pictures, whether in your head or scratched on a piece of paper or on a computer, those pictures, if you read the pictures carefully, tell you exactly what the definition says. And I think that's really important. You don't take a definition and decode it. You take the concepts and explain what you mean, express it as a logical definition. Before I go any further, I should say infinity plus infinity. You know, these are the sorts of things you don't prove very often, but now that we're dealing with everything as sort of parallel objects, you can prove these. What is infinity plus infinity? You can not only say that it is, well, I hope everyone sees that looks like infinity. You can not only say it's infinity, but you can prove it. How would you prove it? Well, plus infinity. The same as you always do. How does it go? Start with your target. Quantify that with M. No matter how far my target squeezes, no matter how big M is, my little chasers, plus infinity and plus infinity, should be able to squeeze far enough. There exists an N1 and an N2, so that if I take any point x in the first plus infinity and y in the second plus infinity, and I add them, here's the results, those results should hit my target. In other words, x plus y should land in the target. X plus y should be bigger than m. Okay? This is, again, a very easy proof, which can be done if you know, students, or if a professor wants their students to be doing the epsilons and deltas and for alls and there exists, you can do it. Or you cannot, right? You don't have to do the quantification. You can see it, and you can prove it and define it if you want to. Okay, depending on the level, of course, and the time involved. Okay. One last, just quick remark. You seldom would do this, but plus infinity plus, say, negative infinity. What's the result? Well, it's one of these indeterminate cases. In fact, all real numbers, if you think about it, take big positive numbers and add them to big negative numbers. Depending on which ones you take from the plus and which ones from the minus, you get different results. In fact, you get every real number. You can think that through yourselves on your own time. The answer would be the interval from negative infinity to infinity, the whole real line. You could prove something like this if you wanted to. You typically wouldn't, because why would you prove an indeterminate result? You'll never use an indeterminate result in general. You'll go back and try and change your expression to get a good result. But if you wanted to, you could. There's no need to quantify the target because it's constant, so you jump straight to, can my plus infinity and my minus infinity squeeze far enough so that the sums of those numbers fit inside? This is a silly one. Perhaps this wasn't even worth doing. But at any rate, for any target painted, and there's only one target, so don't bother, I should be able to squeeze my chasers far enough so that if I add them, if I take any point x in my plus infinity and y in my minus infinity here and add them, that number x plus y can hit the target. Well, the x plus y is a real number. If you think about this, this is a vacuous statement almost and not much to prove. But you could. All of these objects, whether basic or not basic, have definitions, and you could write and prove these definitions. On top of that, you can also think about these concepts without the definitions and use that to understand how to write them from scratch.